Hello again, this is Wayne Schaefer coming to you from my basement workshop. As you may recall, my first presentation covered using simulation as a tool to teach skills in programming and automation. This next presentation in the series will focus on a summary of how simulation can be used in the classroom as a tool to enhance lessons in industrial project management skills. In fact, this is basically a 1-hour summary of one of the courses I've developed and currently teach. As in Part 1, I'm still concentrating on the universal design for learning concept of providing options for comprehension, such as activate or supply background knowledge, highlight patterns, critical features, big ideas and relationships, guide information processing, and visualization. As much as I would love to just jump into the simulation portion, there must be a launching point for discussion, especially in the classroom. For this, I start my course by looking at 3 project failures, and with so many to choose from, the selection was very difficult. So in the end, I just picked these 3, and if you ask me why, well, it's because I liked them at the time. Unfortunately, there are so many to choose from, it was a very difficult choice. Now, although I covered these a little bit more detail in class, I'll give you a brief overview here. The first one being the Denver International Airport. The second, the National Health Service in England, and the third, a blast from the past with a project IBM did in the 1950s. So the first one, Denver International Airport's automated baggage system. So who failed? Well, the Denver International Airport failed. At the time, the largest airport in the United States by total land area and the 6th biggest in passenger traffic. What were they trying to achieve at the time? Well, they wanted to upgrade their time-consuming luggage check-in and baggage transfer system, basically fixing barcodes to all the luggage, and this would result in fully automated baggage transfers, and also integrate all the 3 terminals they had. In the end, I suppose the ultimate result was trying to reduce that aircraft turnaround time significantly. So what failed for them? Well, they basically had a failure of all 5 key variables that project managers have to deal with. That's scope, time, cost, quality, and risk. And why did they fail? Well, it was a huge fiasco, and the why can be traced back to the most detrimental oversight, which was to not include the airlines in the planning decisions. And with the benefit of hindsight, we can certainly see how crazy that was. But they didn't include one of their main stakeholders in features such as catering to oversized luggage, sports equipment racks, even separate maintenance racks and luggage systems were not designed properly or not at all. And that led to a large portion of this work being redone and in the end actually abandoned. Failure number 2, the National Health Service in England. So who failed? The National Health Service. It's England's publicly funded healthcare system, largest and oldest in the world. And what were they trying to achieve at the time? Well, they wanted to revolutionize the way technology was used in the health sector, pave the way for electronic records, digital scanning, integrated IT systems across hospitals, and community care. Basically, they were trying to create the biggest or largest civilian computer system in the world. So why did the project fail? Well, it failed because of changing specifications, unrealistic expectations, such as in timelines and costs, inadequate preliminary research, and failure to conduct progress reviews. The last project I talked to my students about concerns IBM and reaching back in time a bit to demonstrate that project failures are not new, and in fact has been going on for quite some time. Anyway, so back in the late 1950s, IBM set out to build the world's fastest and most technologically advanced computer, which they called the IBM 7030 stretch computer. It was supposed to be 100 to 200 times the speed and performance of the nearest competitor with an ambitious price tag of about $13.5 million. So why did they fail? Well, they had overly optimistic forecasts, project timelines and costs that were severely overrun, and engineers were faced with a new challenge at the time, which was to do with ferrite core memory. And the groundbreaking system, which was a load-sharing switch, would allow the use of transistors to drive the ferrite core memory, and this was amongst one of their biggest problems. Bit of a silver lining here, though. The manufacturing, packaging, and architectural innovations at the time helped catapult IBM to the forefront of the industry. And if it wasn't for the lofty expectations that they set for themselves at the time, this would have actually been a success. So as a quick lessons learned summary, if we look at the Denver International Airport, they didn't include the airlines in the planning, resulting in costly replanning and delays. IBM had overly optimistic forecasts. The National Health Service in England was faced with changing specifications, unrealistic timelines or unrealistic cost expectations, and inadequate preliminary research. All of these projects could have benefited from better communication and planning. The problem is that many projects start with a statement like, hey, let's build the cheapest car in the market and build it in record time. So the takeaway from here for my students is that talking with all the stakeholders or shareholders to understand what is expected is very, very important. And this goes a long way in achieving the most important part of the process. If we go back in history, we find out that in many instances, there were just not enough communication happening between the right people. I suppose with that being said, lack of communication is not always the case, and maybe sometimes we just don't know what to ask or who to ask or what questions to ask. But a lot of these major failures do fall down on the communication side of things. So how do we address all this? Well, it can be argued that projects discussed previously failed primarily due to failures in project management that can be traced back to the initial stages of determining operational parameters, such as what did the customer want? Was the program technically feasible? Were the costs and timelines correct? Sure, there are other factors such as pressure from upper management, but that's stuff that we can't control, so we're not really discussing that too much in this course. Communication with the customer is key to a successful project and a good project management team. However, there are also many times the customer does not know exactly what they want. If we take a look at traditional project management courses, we teach techniques in project management fundamentals, initiating and executing a project, time management, setting budgets, procurement and resource management, stakeholder management and communication, managing work, scope, stakeholders and costs, risk planning, controls and documentation, and of course how to close out a project. Now there's a lot of paperwork to create in some of these courses, and much is just a theoretical exercise. I've had some of these courses and we generate a big document of some fictitious project and try to iron out our project management skills this way. Now there's nothing wrong with that, but I want to apply these skills to industrial project management, and based on my experience, it doesn't always flow over very well from traditional project management to industrial project management. Students are given many tools during these courses, and there are many at our disposal. A work breakdown chart, for an example, can be used to decompose projects into the component tasks before starting the Gantt chart. Then, of course, we have our Gantt chart, which hopefully everybody is familiar with. The Gantt chart can be used to develop a timeline, which is a good overview of the Gantt process, and can be used for an executive summary. Pareto chart, we can use these when identifying the yield of best return on investment, the lowest hanging fruit, so to speak. Fishbone chart, when trying to identify the cause of a problem, especially when we run into issues where we need to jumpstart the team's thinking a little bit. And back from the Gantt chart itself, if we find a task that's a little bit too complex for the Gantt chart, we can use a PERT chart to break down the complexity of that task. Now all these are just tools, and you don't have to use them, but they're available for project managers to make use of. And all these tools, of course, we can teach theoretically in the classroom setting. Unfortunately, student experience is missing what can only be taught from working in the field. So if we take a look at traditional teaching techniques, the problem, as an example, given a set of requirements, develop a project specification. Large part of industrial project management is not emphasized enough during these exercises, such as let's look at the problem statement to develop operational parameters, specification resulting in some sort of a design. Let's take a look at our requirement solicitation. What does the customer actually want? Traditional courses do not give the students experience enough to avoid the pitfalls of the three examples that I cited above. After taking my master's in information technology, I decided to try to integrate traditional project management with tools developed for software management. Coincidentally, when I began my master's, I mentioned this to one of my professors, and he chuckled and said that he had never heard someone apply software management skills to industrial projects before. So I thought, why not? Since I had to develop the course anyway, I attempted to put these tools together to give the students more options and opportunities to succeed. Some of the tools we're talking about here: requirement solicitation, how we gather information out of the customer. How do we make sure the customer knows what they're asking for? Once we do all the workshops and brainstormings and interviews, the team can develop what we call architecturally significant requirements. And by the way, again, these are just tools. There's no requirement to use them all. It's just, what's available to us at the time. Use cases can be used to map how a user interacts with his environment and how the process interacts back with the user. This can be mapped out especially if we're not really sure what's driving the request in the first place. We may want to go back to upper management and use a technique called the pedigreed attribute elicitation method, or POM, to elicit business goals out of the company. Let's see what they're actually asking for from a business side of things. All this data feeds into what is called a quality attribute workshop. This is where we develop stories, measures, and we try to quantify the data and define relationships. The output of the quality attribute workshop feeds into a utility tree, which is basically a summary of all the stories that were developed previously. Now, some refinement can be done using an architectural trade-off analysis method, and then fed back again into the utility tree. If we think of industrial projects, especially those projects that have a lot of programming involved in, why shouldn't we be doing something like this? That's really the question we should be asking ourselves. So, of course, I put it in this course, and this is what I'm running with. If we take a look at working with projects, let's divide the section simplistically up into 3 parts: business and mission goals, architecture, and the system to be created. Now, the business and mission goals are used to design the architecture, and the architecture must, of course, satisfy the business and mission goals. Once we have the architecture in place, it's used to implement the system itself, and again, we have to check back to make sure that the system conforms with the architecture we originally set out. So in that, we have 2 iterative cycles occurring. One is the design cycle on the left side, where we ensure that the mission goals support the architecture and the architecture supports the business goals. And on the right side, there's a similar loop between the architecture and the system. So that means that any change in business goals, architecture, or the system must be continually checked to ensure that the other 2 parts of the project are being met. So this presents a unique difficulty, and we can't lose track of either of these cycles. And basically, it's a live document that we create during the continuation of the project. So the challenge here is to ensure synchronization between what the customer wants and what we can deliver. Now, it's a good idea at this time to mention what experience and education the students have had up to this point. Even so, it's difficult to even know where to start when faced with an industrial project, and many have challenges with this because of lack of experience in the field. Now, they've had PLC and HMI programming. There's been 2 courses by this time. They've had AutoCAD, including AutoCAD Electrical, 1 course in robotics, and 1 initial course in projects. During this course, we actually do a 6-week session how to properly use Microsoft Project, including resources and timelines. So they have a pretty good handle on the tools they need to create the project in the first place. So again, the challenge here is, how do we start the process? How can students practice, and what can be used to enhance the learning experience they've had up until this point? So the first thing we're going to do is take a look at lab number 1, which is called the sort by color conveyor system. The challenge here for the students is to create a specification. The idea is to give them the task of more fully developing and documenting the sort by color conveyor system. The premise is that the sort by color conveyor has been proposed by the technology department as a training tool for teaching and automation. A prototype has been developed and constructed, but is not fully debugged or even in fact operational. So the student teams are required to use photos of the basic prototype and also simulation that we provide to develop a more complete specification that can then be used by an outside firm in quoting an actual trainer. So basically, we've made a prototype with a created simulation knowing that we're going to put this into a project specification that a professional firm can use to quote a new system for us, and that's what they have to put together. So the opportunity for the students is to take what they've learned in their previous PLC and project management classes and apply it to the design phase of a project. From a business goal perspective, we want to ensure the product is sorted by color before shipping to the customer. Architecturally, we want to design a conveyor belt that sorts cubes by color. The problem here is that at a high level, this goal in architecture definition does very little to actually help us design the system. So to address this problem, we have this prototype to help answer some of the more detailed questions, and a simulation to clarify and help students picture what is supposed to happen, and also to maybe look at some options. So in this case, rather than show them the prototype itself, we show them photos from the prototype. So at the beginning here, we have a load position with color sensor, followed by a load cylinder which pushes the blocks onto the conveyor itself. A part tube where we load blocks into to be sorted. We have a reject bin at the end of the belt, and of course a belt feeding blocks down the conveyor itself. If we take a look at the conveyor, there's 3 receiving bins, a yellow, red, and blue receiving bins, and there's 3 eject cylinders to push the blocks into the bins. One last thing we look at is the coupling and rotation procs that can be used to count revolutions and determine the position of the belt and therefore the cube on the belt. Along with traditional project management documentation, students are required to complete the following. They have to create a project scope and specification containing operational parameters, a parts listing, a drawing or sketch of the system, basic I/O listing and prints, controls definitions, auto, manual, enunciation, that sort of thing, and of course any other options that they can think of. As part of the enhanced approach to creating the project specification, the original class assignment discussion begins by reviewing photos of the actual physical prototype, and then they're required to view the simulation modeled from that prototype. So this way they can start the project by considering physical connections, interconnections between modules and components, hardware configuration, and real inputs and outputs. At this point, I direct them to view the simulated video posted on YouTube, and I will share that with you here. So I've shaved a few minutes off from the one that I've actually posted, so if you take a look at that one, it starts with a little bit of an introduction. I've cut that out here. The information does go by quite quickly. You may wish to recall up the separate video on YouTube if you want to go back and review it. What I have here is a simulation of the conveyor system we built in one of the labs. A stack of colored blocks is loaded into a tube at the start of the belt. At the bottom of this tube is a color sensor. The sensor sends a signal to the PLC based on the color of the block at the bottom of the stack. Once the color has been determined, a pneumatic cylinder is used to push the block forward onto the conveyor. The motor is then turned on and the block is transported by the belt. One of the 3 cylinders is then used to push the block into the bin designated for that color. If the color is not determined or is invalid, the block would then continue until reaching the end of the conveyor, at which point it is deposited into a reject bin. Once a block has either been unloaded into one of the 3 bins or rejected, the cycle can be repeated. Processing one block at a time helps keep the programming at a fairly basic level. The actual conveyor system doesn't quite have everything shown here, such as individual part-present proximity switches, but it does have a proximity switch that pulses twice for every rotation of the drive sprocket. This can be used to determine the position of the block as it travels along the conveyor. So let's go ahead and start this thing up, and I've given you a window view of the panel so you can see what I'm doing. First of all, we have to adjust the speed and turn on the conveyor, and we're going to leave the setting to use the part present sensor instead of the encoder to locate the part. I've left the encoder count displayed on the screen so you can see the position the belt stops at for each of the colors. And this turns out to be about 71 for blue, and you're going to see 112 for the metal and 32 for the green. I mentioned the conveyor speed adjustment before. We'll come back to that later. For now, I've adjusted the speed so that whether we use the encoder or part present, it doesn't have any major effect on where the part stops. And we're going to switch to an overhead view. The overhead view shows that the belt stops distance about a quarter way down the width of the part. The time to stop is a combination of the processing time, communication time, and a 100 millisecond debounce timer I've added in the logic. Again, like I said, I've chosen the belt speed that minimizes any negative effect caused by selecting either part present or the encoder, so they'll stop in approximately the same place, and you're going to see that in a minute for the encoder. Now I'm going to show you a similar sequence. However, as an alternative, we're going to select Use Encoder. Then we're going to adjust the speed similar to what it was in the previous example. And then we're going to turn on the conveyor. In this mode, once the part color is determined, the target position is displayed and the PLC uses this value as the stop point. Now, because of some delays in the system, the belt could actually stop a bit after the set point, so I've actually created a stop window of basically the set point plus or minus 2. I think this is a good representation of our lab conveyor, with the added bonus now of being able to add and experiment with part present sensors. You can see the target there was 112, and it actually stopped at 112, so it was pretty good there. Again, as you can see by the overhead view, the part stopped relatively in the same place. I turned off the indicator that shows where the part present switch is sensing, just kind of to drive home the point that this is using the encoder. In the next video, I will show what happens when the conveyor speed is fast enough to become a significant factor as to where the part stops. But to keep this short, we'll stop here, and as always, thanks for watching. Okay, hopefully you enjoyed that video. Now, what were the results? Well, students can see and understand the need for both the physical prototype and the simulated environment, and also appreciate how the changes in operation can be simulated. Other possibilities that could be simulated, which we haven't seen yet, we could do missing or defective switches in the simulation. Could actually take a switch out or misalign the switch and see what happens. We could set the encoder window too small just to see what would happen. Will the part just fly by the position? Will it stop properly? Will it jam up? Will it cause the system to lock up? You know, what could happen? What if the target is in the wrong place? What if we move the proximity switch into the wrong position? What would happen? And again, what would happen if the parts are moving too fast to push? So if I've sped up that conveyor, which I haven't shown here, and the parts are moving too fast, can they actually get pushed? Will they slide on the conveyor? What will happen? And that's one of the videos I haven't created yet, is to show what happens when the conveyor speed is increased, which is something I can do with the existing simulation by just turning up the potentiometer. One nice thing about the simulation is I can test, break, or fix the system inside the simulation without ever having to touch a physical system. Remember that many of the students haven't even seen some of this equipment, so being able to see the simulation gives them first-hand view into a real industrial environment. So without the simulation, students would have to rely on their imaginations, and with little or no real-world industrial experience to lean on, that's pretty difficult. They can't test ideas, and it would be much more difficult to demonstrate ideas to other stakeholders. So they may have a great idea, but without a simulation to try it on, they can't demonstrate that idea to someone who may not quite understand what they're talking about at the time. I have noticed once they see the simulation, you can already notice some recognition of problems and realizations of solutions. As far as exploring options go, sure, you can argue that technologists, technicians, and engineers can test ideas during build or that prototypes can be used, but what if the idea causes damage to the system? Or there's an expense for a builder or customer that does not provide a payout. In industry, for example, we had an idea such as variable speed assembly lines, and these added huge expenses to the assembly system, and it ended up having virtually no impact on the throughput of the system. So to find that out early would certainly be advantageous. So it's difficult to assess the pros and cons in advance. Another thing we have to think about when we're implementing systems without simulation is to have a fallback option. You know, what happens if what I'm trying out doesn't work? Can I put it back to the original system? Especially if I'm working on a piece of equipment that's already in production. There always has to be a fallback plan. And in cases of where we haven't designed properly in the first place, we might be stuck with substandard equipment and have no way of changing that. If I can simulate that in advance, then maybe I can find the shortcomings of that system beforehand. So in the end, simulation allows students to go through this process, test ideas without ever having to touch a real system and worry about jamming something up or breaking something or worrying about the cost of that system. So this brings us to the second lab that we call the sort by height conveyor system. The process for lab 2, in this case the assignment has no physical prototype, only a concept and basic simulation. The opportunity here is to take what was learned in PLC and project management classes and apply to a purely conceptual design phase of the project. The task here is for the student to use what could be learned from simulations to create a project specification in order to propose several solutions to the customer. The desired outcome is to show how simulation can be used to enhance project and project management discussions to a level typically not achievable by traditional methods. So in this case, we have an emitter here, and this is used to drop pallets onto the conveyor automatically. The conveyor and motor that moves the box and pallet along the conveyor to this set of sensors here. And this set of sensors detects the height of the box that's sitting on top of the pallets. Then the pallet moves on to this lift and divert mechanism here, which can shuttle the parts left or right depending on the size. There's a sensor that detects that the pallet is in place on the diverter. There's also sensors for entry to the right-hand conveyor system and exit from the right-hand conveyor system, and also for the left side entry and left side exit system. In the case of the simulation, we have automatic removers for the right-hand side and automatic removers for the left-hand side that will take completed pallet and box assembly out of the system. So this is just a list of everything I just went over on the previous slide. So here I give the students an overhead view showing the expected inputs. And this could have been done on a layout as well, like on an AutoCAD layout, but I think it's a little bit more realistic looking if I use the projected view from the simulation itself. So here we have the auto, manual, emergency stop push buttons, the start stop push buttons, and a reset push button that come with the simulation, and that's all mounted here on this panel. For the sensors, I have a high sensor, a low sensor, and a pallet sensor. Pallet loaded capacitive sensor, at left entry to reflective sensor, and at left exit. I also have at right entry retroreflective sensor here, and at right exit retroreflective sensor here. There's also a few inputs that come from the simulation to the PLC. As we're doing the programming, we can use that as part of our simulation, factory paused, reset running, and the time scale the factory is actually running at. I can slow the factory down, and I could use that time scale to offset timers in the program if I wanted to use it at half speed as an example. Then some of the timers may not work properly at half speed, but I can adjust the timer base by using this time scale. This is a separate overhead view. I want to show the outputs. In the case of the panel, I have a stop light, a reset light, and a start light. The emitter can be controlled as well, so I can turn the emitter on and off to drop pallets at whatever speed I want to drop them at. I have a motor on the entry conveyor. I only use the load motor in this case to bring the pallets onto the divert system. A transfer left signal for this lift and divert mechanism, and also a left conveyor motor. A left remover, in this case we forced it on all the time, so whatever pallet moves into the remover, it'll be removed automatically. We could control this depending on the type of simulation we use. Transfer right signal for the diverter, right conveyor motor, and a signal for the remover as well on the left hand side. I have several objectives for this project. In objective number 1, I use the emitter to drop pallets and boxes on command only. We move a single pallet along the conveyor. We detect the size as it passes through to the diverter. Then we shuttle the pallet left or right depending on size, and we wait until the pallet leaves the system before we reset and release another part. So I'm going to go ahead and show you a video of the operation here. It's a little bit choppy. The sound isn't quite synchronized. I just turn the sound off here. So we're going to go ahead and turn it into automatic mode. Start it. The pallet and box come along the conveyor. Go through the height detection system onto the diverter. It's detected that it's a low box and it shifts it off to the left. As soon as it hits the remover, it dissolves and disappears, and a new box appears at the emitter. Notice I'm only doing one box and pallet at a time. Now I've detected a high box and it moves it off to the right. Basically, as soon as I see the exit sensor get tripped, I create another box and pallet. So you see one box at a time, and I don't create another box until it's left the system. Okay, so we take a look at the advantages for this. We notice that all the conveyors can run with the exception of the diverter left and right motors. It's very easy to program, moving one pallet and box at a time. It's easy to program faults. Again, same reason, using one pallet and box at a time. It's easy to recover. If the system goes into e-stop, it loses power for some reason, can't remember what it's doing, all I have to do is remove that pallet, reset the system, and restart. No problem. So because of this, there's very little, actually there's no need for any memories to track pallets on this kind of system. The one disadvantage we have, though, is the throughput of the system is minimal. And the constraint here being that the speed of the conveyors dictate the throughput. The constraint is something that we can't change in the system. From an educational perspective, this is very easy for the students to understand because we can actually show the system in operation. The other nice thing about using the simulation is I can create an I/O table, which is also important when planning and programming. So because I have everything in the simulation I've had to set up correctly, I can automatically generate an I/O table from that. So that's just kind of an aside there. So now we tell the students what happens if the customer changes their mind. Well, what if they're going to remove some requirements or add other requirements? So in this case, we come up to Objective 2. In Objective 2, we want to drop the pallets or have the pallets enter the system on command only, same as we had before. We're going to move a single pallet along the conveyor. We're going to detect the size as it passes to the diverter and then again shuttle the parts left and right. But instead of waiting until the pallet leaves the system, for this option we're going to wait until the pallet leaves the shuttle. At that point in time we're going to reset and release another pallet to the system. So now I have a video of that operation as well. Let's put the system on automatic mode, start it. We move the box and pallet along. Gets detected onto the diverter and it shuttles it to the right because it's a high box. But as soon as it enters the right or left conveyor, I can create another box and pallet. It's basically like giving whatever system is loading that box a clear to load signal. So I think it's pretty easy to see how the system is operating now. As soon as that box and pallet shuttle and it enters the left or right conveyor, I get to create another one. So in this case, I've got the low box going through, it'll shuttle to the left, and as soon as it makes the proximity switch, I create another box. Okay, I think pretty easy to understand. So now we take a look at the advantages of option number 2. And again, all the conveyor motors again can run continuously with the exception of the diverter left and right motors. It's relatively easy to program, and again, moderately easy to program faults. We only have 2 pallets on the system at any one time. It's fairly easy to recover. Similar to what we had before, we remove the pallet, reset, maybe even finish the transfer if required manually, but in general it's still fairly easy to recover, and there's very little need for memories again to track these pallets. From a disadvantage perspective, we can see that the throughput of the system is still not optimal, and our constraint is the same, that being the speed of the conveyor dictates throughput. However, sequencing did provide some improvement. Customer changed their mind again, and this time it's more of a major change in operation. So for objective number 3, we're not going to wait until the pallet leaves the shuttle. We're going to allow pallets to arrive as quickly as possible. And you notice I moved those to the top of the list because there were major changes in operation, so I wanted to highlight them right away. So the emitter is going to drop the pallets and boxes automatically and continuously now. We're going to move multiple pallets along the conveyor. We're going to still detect the size as it passes to the diverter, but we're only going to allow one pallet on the diverter at any time, but clear as soon as possible. Shuttle left and right depending on height still. I have a video of that last operation. System in automatic mode. Press cycle start. And now I start loading pallets and boxes as quickly as I can. Now you'll notice one change in operation. I have to stop the in-feed conveyor. So as soon as the pallet is loaded onto the diverter, the in-feed conveyor has to stop to allow me to divert that box left or right. But as soon as that box and pallet is clear of the diverter, I can shuttle the next one in. Okay, these all seem to be high boxes and they're all diverting to the right. Now you will notice once the low box goes through, I have 3 pallet and box combinations in transit at one time. One going left, one going right, and another one going into the diverter. So you get a sense here that there's a certain level of complexity increase with this change, which is why I called it a major change to the system. Now the advantage here is we can handle much faster throughput, but that's about the only advantage. Now we start getting a lot bigger disadvantage list that goes along with it. The conveyors must stop and start to control the traffic. So that adds wear and tear on the hardware, that adds wear and tear on the electrical components. It's much more difficult to program because we have to handle multiple pallet and box combinations at a time. We have more risks of faults, hang-ups, and collisions. Now that we've got pallet after pallet coming onto the system, it's much trickier to recover. You know, what if I use the same methodology as I used in the first 2 options? I have to remove all the pallets and boxes in order to restart the system. That may not be a very good idea anymore. So now we're talking about possibly the need for memories to track the pallets. If I e-stop just as a pallet is diverting left or right, can the system recover? Can it remember that it was diverting left and right if I leave the pallets on the system? You know, we have lots of more issues that we have to get resolved at this point. So here's a question I ask all my students, and I'll ask you as well. Which of the 3 do you think is better? Now I also asked my students, what did you notice as we transitioned from one set of requirements to another? Now I won't show it here, but I do have the ladder program for the students, and I show them this when I'm asking them this question. But these are the 2 questions I ask right after I show them the 3 methods. So I'm going to give you some time to think about it here and see if you can answer these questions. Now, unfortunately, I didn't tell you it's a bit of a trick question. Which of the 3 are better? It depends on the customer and their requirements. A lot of my students say, well, option 3 is better because it has a lot better throughput. But what if the loader can't load pallet and boxes any quicker than 1 per minute? And why would I need to run the system in number 3 mode, add the memories and the complexity, all the faults required, the start-stop issues that we have to deal with for the in-feed conveyor? If I cannot load the parts that quickly, why do I need it? So maybe option 1 is just fine. So it really does depend on the customer. One thing you didn't see is the programming style I used allowed for easy changes as the requirements changed. I'm not going to show that here, but it's just something that we do in class as part of this exercise. So the challenge here for the students is to create a specification with these options in mind. Now the students are required to complete the following for this task. They have to create a main panel for their design, which will include a main panel with push buttons and indicators for auto, manual, and mode reset, cycle start, cycle stop. They also have to include manual push buttons and indicators for all the conveyors, the diverter controls, for the emitter, which would be indicative of something loading, and include 1 or 2 HMI screen designs that can be used in place of the main panel in case a customer wants to upgrade. The HMI can work concurrently with the main panel, like it doesn't have to replace it, but it can also be used just as an enhancement. Now imagine going through that list without being able to see the simulation beforehand. It'd be much, much more difficult. So from the student perspective, after they reference the existing simulation, they have to create a basic AutoCAD layout showing the equipment locations, control panel and HMI positions, interfaced automation, load and unload points, I/O points located around the equipment layout, and they have to come up with a description of operation for each area and possibly interfaces between the conveyor, buffer, load-unload zone, that sort of thing. They also have to develop a timing and installation plan with basic resources. At this point, they're going to use Microsoft Project or any other Gantt chart software that they want to use at the time. And remember, they've also had Microsoft Project by this point. They have to generate a bill of material and also do a basic failure mode and effect analysis, which has been covered by this point in the class. They have to look at the interface requirements with possible external equipment or personnel. Remember, in the simulation we had an emitter that created the box and pallet combination and removers that removed them, but in the real world that would be either a robot or a tow motor manual handling system of some sort. So the students have to basically replace the emitter and removers with what they think the equipment would be. And they can come up with anything they want: robots, elevators, personnel, whatever they think is a valid choice to put boxes and pallets on the system and remove them. But they have to give us a description, reasoning behind that system. They can't just put a robot in they have to still explain why they're adding a robot to the system. Why is it a tow motor load? Why is it a manual unload? That sort of thing. They have to come up with a flowchart for the individual machine, and in future projects they have to do the entire plant, which would be made up of multiple machines. A PLC programming plan does not have to reference a specific PLC type, so this would be like language independent type programming plan, including what they expect for subroutines, inputs, outputs, flags, registers, timers, memories, that sort of thing. Now, I don't make the students develop everything on their own. I give the students about 70% of the material they need to do the project. If you take a look at the left here, this original panel, this is what comes with the simulation, and what I give the students is an example of a new panel that could use for the simulation, so they have at least a starting point. Again, imagine doing this without the simulation to start the process, just showing them a simple electrical panel and then a new electrical panel with controls on it without good visual representation of what those controls are used for. Some more advantages to talk about here. We do have the ability to walk through simulation and observe the equipment from an operator standpoint. This provides valuable feedback and allows students to test run projects and gain valuable experience. This could include looking at things like obstructions, inaccessible areas, panel locations, functional issues, warning lights and beacons, safety barriers, and fences. So I'll do a few walk-around videos and give you an idea of what I'm talking about. Just a note here, there's going to be no sound in these simulations. I've turned the sound off, and I'll just be talking as we go through this video. So the idea again is to show you what an operator would see while using the equipment. I'll start the video. Boxes are going along the equipment, and we're just going to drop down to the floor here. So now the operator is going to walk up the stairs, go to the panel, so now they can see the panel. It's going to look to the right, see the boxes coming along the conveyor belt, going onto the weighing scale, getting weighed, and then moving on to the bubble table. So again, that emitter would be some other interface device of some sort. So now the operator decides, well, let's walk around the equipment. So now the operator is going to walk around the equipment to get to the second remote panel. And now we can see the remote panel, the elevator. You can take a look, see the boxes coming down the conveyor. And we can actually follow the box as it moves on to the stacking area. You notice this little flipper is out. that helps turn the box. When that flipper is back in, the box come in lengthwise. So this is a short video, and what you're going to see is the operator take a look at the elevator operator panel. Then he decides he needs to control the conveyors and notices that the conveyor panel is on the floor, and we'll see what happens here. So the operator looks at the elevator control panel, notices that the other panel is on the floor. There's no way to get there. Realizing he has to turn 180 degrees around and walk all the way back along the conveyor system here. So for walkthrough number 4, this is the operator that decided he needs to get to the other control panel. We're starting at the main panel at this point. We're going to walk down the stairs, walk along the raised platforms, heading towards the remote panel that's mounted on the floor level. So the operator is going to turn around, take a look at this panel, and probably realizes that it's in the right place it should be. He can see the conveyors from this panel. He can see the elevator from this panel. It's just the accessibility that he has to walk all the way around the gantry to get to this panel, which we could point out in this simulation, saying, maybe we need another set of stairs right here to allow the operator to get from this upper panel to this conveyor control panel. So walkthrough number 5, we're going to press the E-stop and then take a look at what the operator has to do in order to get that E-stop to be reset. So the operator presses the restop, notices, okay, now I got to go back to the main panel and do the reset for that E-stop. I'm just going to go up the secondary set of stairs here. It's not the main set, it's the secondary set. Walk along here, and I'm going to run into, an obstruction. So I can't get over this, get around this conveyor, and he's going to do what a lot of operators might do on night shift or back shift. He jumped over the conveyor. Now, it's not saying that they're allowed to do that, but operators tend to do strange things. What we'd like to point out there is hopping over the conveyor obviously is not safe, and it's surely against company policy, but this is where we talk about designing systems to fail. If we would have designed that system better, the operator wouldn't be forced to jump over it, and we wouldn't have created the safety hazard. So sometimes we design systems to fail without even realizing it. And the simulation will help you walk through and take a look at systems from an operator standpoint. Okay, well, the operator's at the panel, so let's go ahead and restart the system. So the operator takes a look around. Okay, everything looks fine. He presses auto cycle start, and we're going to find out, this guy's kind of inexperienced. He didn't reset the system properly. We've got a box stuck on the conveyor here. We've got a jam up occurring. We've got faults. He's noticed there's a problem with the elevator, so now he's running around the decking here to take a look what's happened to the elevator. We've got boxes on the floor. We got boxes stacked up improperly. We got some boxes on the conveyor. The elevator's coming up. It's jamming up. You can see the boxes bouncing around here as it's pushing up against the doors. Now we got boxes falling off even further, and pretty soon we get an elevator fault here as well. So I can kind of show you what would happen if there was an inexperienced operator on the system. He doesn't know how to start it back up again. Or we could look at it from the standpoint is, if I have an inexperienced operator, how do I start the system up and make it safe? Maybe there's a lot more memories and reset procedures that have to be developed at this point. So the simulation itself is an excellent tool to help avoid the pitfalls of some of those 3 examples that I showed you earlier in the presentation. It provides the ability to walk through a simulation and observe from an operator standpoint. Controls we can provide help them run the simulated operation, and we can also include fault handling and reset capabilities. And all in all, this provides valuable feedback for the students to test run projects and gaining valuable experience. And again, this can also be a tool that can be used to talk to the customer. So that's it. Hopefully you enjoyed this and it was informative. Thank you very much for watching. Bye-bye.